going to solve problem 9 from your homework last night. So in chapter 6, problem 9 is on page 152, and it reads, a softball is tossed into the air at an angle of 50 degrees with the vertical at an initial velocity of 11 meters per second. What is its maximum height? So I've drawn a picture of this scenario to get started. We have a softball being launched into the air, and we're trying to find the maximum height. So our maximum height is going to be up here. It's going to be at the very top of the softball's path. The problem also states that our initial velocity is at an angle of 50 degrees from the vertical. So let's draw our initial velocity triangle and consider this. So if our initial velocity is from the vertical, we're going to start in the vertical direction and then move 50 degrees. So this angle would be 50 degrees. Now up until now we've been considering our angle from the horizontal. So let's find what that would be so we can be consistent. So if we're 50 degrees from the vertical, that would mean our angle above the horizontal is going to be 40 degrees. 40 degrees and 50 degrees sum to 90 degrees. So in this case, 40 degrees is our theta. Our initial velocity that we were given is 11 meters per second. That's going to be our hypotenuse of our triangle. Our 11 meters per second is in both the horizontal and the vertical directions. So now we need to break this vector down into its horizontal component and its vertical component. To find our initial velocity in the horizontal direction, velocity initial x, we can use a trig function. This leg is adjacent to our angle, so let's use cosine. Cosine of our angle theta, 40 degrees, is equal to our adjacent leg, which is initial velocity, horizontal direction, times our hypotenuse, which is 11 meters per second. We can solve this for our initial velocity in the horizontal direction by multiplying both sides by 11 meters per second. Make sure your calculator is in degrees mode, not radians, and you can solve this for velocity initial in the x direction. I got 8.45 meters per second. We can also fill this value in over on our table. So I've written down all of our variables. We can plug in 8.45 meters per second for our velocity initial in the horizontal direction. Now let's find our initial velocity in the vertical direction. For this one, we can use sine. So sine of our angle, 40 degrees, is going to equal our opposite leg, which is velocity initial in the y direction, over our hypotenuse, which is 11 meters per second. Solving this for our initial velocity in the vertical direction, we get 11 meters per second times the sine of 40. Solving this for our initial velocity in the vertical direction, I got 7.07 meters per second. This value would go over under vertical on our table of initial values. 7.07 meters per second is our initial velocity in the vertical direction. So now that we've broken down our initial velocity, let's consider our other initial conditions. In the horizontal direction, let's take a look at our initial position. So we're throwing this softball, and we're starting on the ground. So I'm going to call our starting point 0 in the horizontal direction. 0 meters. So looking at the horizontal axis, we're starting at 0, and then traveling a certain distance. We're not sure how far this is going to go in the horizontal direction, so we can leave that as a question mark. For the velocities in the horizontal direction, we just found our initial velocity. Now for the horizontal direction, we know that the acceleration is going to be 0 meters per second squared. So we don't have any acceleration in the horizontal direction. So if we don't have any acceleration, we know that our velocity is going to remain constant. So our final velocity, that should be an F, our final velocity in the horizontal direction is going to be the same as our initial. 8.45 meters per second. That's all of our information for the horizontal direction. Now let's turn to the vertical direction. Let's consider the vertical position. Initially, you're throwing the softball. Let's call that initial point 0. We're starting at 0 in the vertical direction. And we're throwing the softball up, and we want to know that highest point. So that highest point, that's going to be our final position. Our final position in the vertical direction is going to be the highest point, and that's what we're solving for in this problem. So that's an unknown. I'm going to put a question mark, and I'm also going to circle it, because that's what we're asked to find in this problem. Now we can turn to our velocities in the vertical direction. We found our initial velocity for 7.07 meters per second, and our final velocity. Well, let's consider this situation. We're throwing the ball up to its highest point. So in the vertical direction, as this ball travels upward, it's going to be slowing down and then instantaneously stopping at the very top of its path. So at the very top of this path, when it's at its highest point, our velocity in the vertical direction is going to be 0. So this is just like when we were talking about free fall. We were throwing a ball straight up, and at the highest point its velocity was 0. It's the same for our vertical direction. The highest point, velocity is 0. So we know for this case our final velocity is going to be 0 meters per second. Now our acceleration for the vertical direction, that's always our acceleration due to gravity. That is going to be negative 9.8 meters per second squared. We defined up as the positive vertical direction, so our acceleration is going to be negative. Now let's look to our common variables. We know that time is common between the horizontal and vertical directions. For this case, we're not sure of the time. We're not given the time yet. Theta is our launch angle. So the angle that this ball was launched at originally, we found to be 40 degrees. It's 40 degrees above the horizontal. Theta was our angle from the horizontal. That's 40 degrees. So now that we have all of our information, and we determined that what we're looking for is our final position in the vertical direction, our YF, we can turn to our kinematic equations. If you look in your books on page 79, we can look at the equations and try and find one that's going to work for us. Since we know we're looking for our final position in the vertical direction, there are two equations that could be helpful for us. I'm going to write the two equations and talk about which one we want to pick. our two kinematic equations that contain the variable we're looking for, our final position in the vertical direction. Let's look and see what information we have to determine which equation we want to use. So the first equation I wrote, it's our position equation. Okay, so final position, that's what we're looking for. We don't know that. Our initial position, we do know that, so that was 0. Our initial velocity in the y direction, we found that. Time, we're not sure of time yet. So now we have two unknowns. Since we have two unknowns, let's put this equation on hold. Let's try another one, see if we have a better equation to use. So now I'm going to turn to our velocity squared equation. Let's see how many knowns and unknowns we have in this one. Final velocity in the y direction, we know that, we said it was 0. Our initial velocity in the y direction, we found that, that's known. Our acceleration in the y direction, well, that's a known as well. Final position in the vertical direction, that's what we're trying to find. And our initial position in the vertical direction, that was 0. So it looks like we only have one unknown in this equation. So I'm going to choose this one to continue. So let's simplify the equation now that I inserted my zeros. 0 equals initial velocity in the vertical direction squared plus 2 times our acceleration in the vertical direction times our final position in the vertical. Okay, so now let's plug in the rest of the information we have. Our initial velocity, that was 7.07 meters per second. We square that term. Plus 2 times our acceleration, which is negative 9.8 meters per second squared, times our final position. That's what we're looking for. So let's solve the equation for our final position. I'm going to bring this term to the other side. So we'll have negative so now we have the opposite of 7.07 meters per second squared is equal to 2 times negative 9.8 meters per second squared times our final position. So now we can divide both sides to get our final position alone on the right-hand side. That side cancels out, and we're left with our final position on the right-hand side. If we simplify the left-hand side, we get our answer for our final position of about 2.6 meters. So our final position is about 2.6 meters above the ground. So that's the highest point. At its highest point, our softball is 2.6 meters above the ground.